Hi everyone, this is exercise 5.2, which is on motion without resistance. This is really just expanding on a lot of the things we've already learned at this point in this exercise. I'm not doing the whole exercise in one video, and this is really quite similar to what we were doing in the simple harmonic motion exercise. So in this exercise, they do tend to use X for displacement, V for velocity, and A for acceleration. I know we talked about that A being a little bit confusing when you do simple harmonic motion because of the A used in the equation, but in this exercise, they do tend to use it. So remember our average velocity. This can be a little bit confusing because we're used to seeing change in Y over change in X. But X is kind of like the Y in this situation, and T is like the X normally would be. So the difference in the X over the difference in time, it is just the gradient formula for average. So the instantaneous velocity, on the other hand, is the derivative. And then also we've got average acceleration in the same way, which is the difference in the velocity over time. And instantaneous acceleration, I've just given it as dv dt here, but also we do have those other forms. Okay, so those other forms of acceleration, it depends what our acceleration function is given in terms of. So if our acceleration function is given in terms of time, then absolutely that dv dt formula is really handy. But if it's given in terms of a different variable, so we saw in simple harmonic motion where it was often given in terms of x, we can use the chain rule and find those other formulas that are all on the reference sheet. So if you make dv dt, if you introduce an x in there, dv dx times dx dt. So I've just put an x at the top, x in the bottom. Technically I've multiplied by 1. Now dx dt, well, that's just velocity, isn't it? From up here, dx dt is equal to velocity. So I'm going to put a v instead of that times dv dx. Now, just that formula there on its own, I'm just going to put a box around that, is quite a useful formula. If our acceleration was given in terms of velocity, so if we had a function for acceleration which was a function of v, that formula would be particularly useful. Now, if I just integrate each side of that, using separation of variables, I'm actually going to bring the dx up there with the a. So a dx equals v dv, integrate, and then this right hand side, increase the power by 1, divide by the new power, so I'm just going to put a half in front. We get that other formula that we use a lot, so that the integral of a is half of v squared when a is with respect to x. I'm going to differentiate each side of that, so the derivative of the integral is just a, and that's the derivative with respect to x of half v squared, and that is the one that is on the reference sheet. If we're given acceleration in terms of x, that is the one to use. So in summary, use the dv dt formula when acceleration is a function of time. Okay, whatever's in your denominator here can be a useful thought, but also what's in your numerator sometimes as well. So in this second one, if acceleration is a function of x, you can use this formula. If it's a function of v, then I would always suggest using this formula. And you'll possibly use separation of variables or something like that. This last one you can use when acceleration is a function of x. And it's generally the one I would suggest if it's a function of x over this one, because this one will just end up at that another line further down you're working out anyway. Okay, so we're going to do some examples. So in this one, a particle is moving in a straight line with acceleration a equals 3 minus 2x. Find v in terms of x, given v equals 2 when x equals 1. So we do have a choice of formulas of a equals v dv dx, or a equals d dx of half v squared. Now remember I said if it's in terms of x, that half v squared one is generally the easiest one to use. So a equals 3 minus 2x is the equation we've given. Instead of a, I can write the derivative in terms of x of half v squared is equal to 3 minus 2x. So I've just replaced my a with this formula from the reference sheet. Now I'm going to integrate each side. When I integrate this side, I just get rid of the derivative. I'm integrating each side with respect to x. So that's just that dx, and they cancel, and integral dx on that side. So I get half v squared equals the integral of 3 minus 2x with respect to x. Okay, so let's integrate that. So 3 becomes 3x, 2x becomes x squared, so 2x squared on 2, plus c, of course. I'm going to put it c on 2 because of the half on the v squared. And let's just double everything. So v squared equals 6x minus 2x squared plus c. Okay, so we just need to find the plus c. So our initial conditions were that v equals 2 when x equals 1. So I'm going to plug those numbers into this equation. So 2 squared is 4. That'd just be 6 times 1 minus 2 times 1 plus c. 6 minus 2 is 4. Subtract 4 off each side. That's nice and handy. C is equal to 0. So therefore, v squared equals just 6x minus 2x squared. Now we were asked to find v in terms of x, not v squared in terms of x. So we need to say v equals plus or minus the square root of 6x minus 2x squared. And then looking at our initial conditions, we can actually work out which one it was. Was it the plus or was it the minus? And because v was a positive number, a positive of this square root, it is the positive one. So we do actually know that v is the positive square root of x minus 2x squared because that v is greater than 0. Although we've actually answered the question at this point, I did also want to consider the domain and the range of the function. So the domain is that a thing under the square root must be greater than or equal to 0. If I factorize that, I've got this function. Now that is a parabola, of course. It'll be a concave down parabola. So the function will be greater than 0 when it's between the intercepts. Okay, in this area it's greater than, it's above the x-axis. So therefore x is between 0 and 3, 0 from here, 3 from here. That's the domain of the function. And of course we should be writing that in interval notation. So x is an element of that. We might also look at the range of the function. Now, the function itself, that's actually an ellipse. Now, if you've been doing the old course, you would know that was an ellipse. If that 2 wasn't there, it would be a circle, but it's been stretched in some way. So if you think of your transformations, the x's have been halved, so it's been reduced. So it's kind of like a semicircle, but much taller. So to find the range, we need to know the maximum and the minimum values there. That's 3 and that's 0. Remember, this is the velocity function, not the displacement function. So the maximum is going to happen at 1.5. You could, of course, differentiate the function to find the maximum value. But the range of that function, velocity, the minimum, of course, is at 0. And if I plug 1.5 into the function, I actually get 3 root 2 on 2. So the v in interval notation goes from 0 to 3 root 2 over 2. Okay, this question, a particle moves on a straight line with acceleration equals 3x squared. Initially, v is negative root 2 and x equals 1. Find x as a function of time. So we've got acceleration given as a function of x again. So I am going to start with that acceleration as a function of x formula with the half v squared. So half v squared equals 3x squared. So I'm going to integrate each side of that. So half v squared equals the integral of 3x squared. I'm integrating with respect to x because of this. So that equals x cubed, 3x cubed on 3, so just x cubed plus c again on 2. let's double everything. So v squared equals 2x cubed plus c. And then we can plug in, of course, our initial conditions. And our initial conditions, so when t equals 0, we have v equals negative root 2 and x equals 1. So if I plug those into that equation, if I square my v, I'm going to get 2. Put x equals 1, so 2 times 1 plus c. So that's handy. We do get c equals 0 again. So our formula is going to be v squared equals 2x cubed. So I am going to square root each side of that again. So v equals, I'm going to write it as root 2x to the 3 on 2. Okay, square root in each side. Now, again, that is plus or minus, but we can use our initial conditions to work out which one it is. And if we look back up here, when x equals 1, v is going to give us the negative. So this time, v is the negative root 2x3 on 2. Okay, so the question asked us to find x. So we now need to think about what v is in terms of x. And v is the same as dx dt. Now, again, we've got different variables here. We've got dx dt, and we've got an x on this side. Bringing the dt up, we're still going to have x dt, and that doesn't work. So we've got two choices here. One choice would be to take the reciprocal of each side. A second choice would be to separation of variables, so bringing the x3 on 2 down, bringing the dt up, and that's the option I'm going to go with. Okay, so when I bring the x3 on 2 down, it's x3 on 2 in the denominator. That's the same as, remember, x negative 3 on 2 in the numerator. So negative root 2 I'm going to leave on that side. Your textbook often doesn't. Your textbook often brings the root 2 down as well. I personally don't like doing it that way. I prefer this. And I'm going to integrate each side. You can put that integral here or here. I actually kind of like putting it there, but it really makes no difference. Okay, so let's integrate this side with respect to x. So negative 3 on 2 needs to be increased by 1, so plus 2 on 2. So that's x to the negative 1 on 2. I need to divide by negative half, which is the same as multiplying by negative 2. And on this side, the integral of dt is just t, so negative root 2t plus c. Remember, you can put the plus c on either side, it makes no difference. So let's find that plus c with our initial conditions. So we were told that initially, when t equals 0, that v equals negative the square root of 2 and x equals 1. So let's go ahead and plug those in. So when I plug x equals 1 here, I'm just getting 1. So that's just negative 2. And that is equal to t equals 0, so this is 0. So c equals negative 2. So our equation at this point, now I'm actually going to go back and just write this in third form. So we've got negative 2, negative power, so over the square root of x equals root 2t minus 2. So the question asked us to find x as a function of time, so we do need it to say x equals. In order to do that, I'm actually going to start by flipping each side just to get x into the numerator. So root x, I'll just leave the negative at the top, over 2 equals 1 over, I'm going to put negative at the top, I'm going to factor a negative out of that, so root 2t plus 2. And then I'm going to multiply each side by 2. Actually, let's multiply by negative 2, so root x equals 2 over root 2t plus 2. So the last thing we need to do is just square each side, but just before I do that, I don't actually really like the root 2 being in front of the t here. Look, technically we can leave the root 2 in front of the t. If we try and rationalize this, the 2 ends up becoming a root 2 anyway, so it's not that big a deal, but I am going to do it. So I'm going to multiply the top and the bottom by root 2. So I'm going to get 2 root 2 So root 2 times that is 2t plus 2 root 2. And we can see there everything's a multiple of 2. So that equals root 2 over t plus root 2. So the last step is just to square each side. So x equals, so root 2 squared is just 2 over t plus root 2 all squared. So that's the answer to that question. Okay, so in this question, a particle is moving in a straight line with v squared equals 6 plus 4x minus 2x squared. Find acceleration in terms of x, describe the motion. Okay, so it's really handy that they've actually started by giving us v squared. If we make it all half v squared, it's even more handy. So let's find out what half v squared is equal to. So we're just halving everything. So 3 plus 2x minus x squared. And remember, half v squared is equal to, the derivative of half v squared with respect to x. I'll write this down. A equals the derivative with respect to x of half v squared. So what we need to do there is just differentiate each side. So actually let's write it like this. So instead of half v squared, we'll write that function. So 3 plus 2x minus x squared. And that equals, we're differentiating. It's very easy here to accidentally integrate. We are differentiating, so the 3 becomes 0, the 2x just becomes 2, and minus 2x. So acceleration is 2 minus 2x. Now, in terms of being able to describe the motion, when you've got a negative times your x, you really want to start thinking simple harmonic motion. I'm going to factor out a negative 2. So it's negative 2 times x minus 1, right? Because negative 2 times minus 1 is positive 2. And that is simple harmonic motion. And we can see that the center of motion is 1. We can see n equals the square root of 2. And of course the period is always going to be 2 pi on n. So 2 pi on root 2, which equals to root 2 pi. We can also remember that the end points of the motion are when v equals 0. So in order to describe that motion properly, we do need to find those. So that's when 6 plus 4x minus 2x squared equals 0. I'm just going to divide everything by negative 2 and write the x squared first. So x squared minus 2x minus 3 equals 0. And that factorizes really nicely as x plus 1, x minus 3. So x equals negative 1, 3. So the particle oscillates between x equals negative 1 and x equals 3. So the amplitude of that motion is also 2 meters. Okay, so just a really quick reminder, when x is positive, the particle is displaced positively. It might be up, it might be right, but that obviously depends on your frame of reference. If x is negative, particle is displaced negatively. When velocity is positive, the particle is moving in the positive direction. Velocity negative, the particle is moving in the negative direction. If acceleration is positive, the particle is being pushed in the positive direction. It doesn't mean it's moving in the positive direction, it's being pushed that way. So if the particle was moving that way and it was being pushed that way, then yeah, it's going that way, it's speeding up. If the particle was moving that way, but something was pushing it back, something's pushing it this way, then it would be trying to move that way, but something would be stopping it, it'd be slowing down in that situation. The particle is being pushed in the negative direction when acceleration is negative. So we've got this example where we're asked to describe the motion of a particle with x greater than 0, x is positive, v is positive, and a is negative. Okay, so as we can see, the particle's position is in the positive direction. Feel free to pause the video to think about these answers if you'd like. The velocity is positive, so it's moving towards the positive direction. It's moving in a positive direction. So if positive is right, it's positioned right of center, it's moving right, the acceleration is negative, so it's being pushed in the negative direction. Okay, so if this is 0, the particle is over here, it is moving that way, but its acceleration is going that way. So the particle is slowing down. And if that force, that acceleration continues in that direction, then what's going to happen is the particle will eventually start moving towards the negative direction as well.